Good afternoon, everyone. Welcome to this third lecture on machine learning for bioacoustics. Yeah, and I don't need to introduce anymore Dr. Emmanuel Dufourq. You've met him already a few times. So, Emmanuel, without further ado, you're welcome to share your screen and start your third lecture. Yeah, and as usual. Participants, if you have a question, just raise your hand or just unmute yourself and ask. We try to keep it as interactive as possible. Yeah. So, Emmanuel, please, over to you.
Great. Thank you. Okay. So let us just remind ourselves of where we stopped on was Thursday last week. Yeah, it was Thursday. Where we stopped on Thursday was we had we discussed the idea of the weights. The neural network are made up of weights, and initially the weights in the neural network are randomly initialized values like -0.1, 0.3. and that we need to update the weights to solve the problem that we're trying to solve. And we update the weights using this expression. The new weight is basically the old weight minus the parameter alpha, which is the learning rate, which dictates how big of a jump we make when we're optimizing. And then we multiply this by the partial derivative of the error. And this is how we will update all of the weights in the neural network. And then I've explained how that we're on this mountain, and when we're high up on the mountain, we are creating a lot of error. And we want to go down the mountain. In other words, we want to minimize the error. And this little graph showed you an explanation why we take the negative of the gradient and how the negative will always make us go downwards. So that's where we stopped last time. But how do we use the data in such a way that we can apply gradient descent and move towards the global minimum? So global minima is just it's a fancy word for saying the absolute minimum point in a landscape, in a function. So we want to go to the absolute minimum. So let's say we have our data and it contains multiple features. In our imaginary data here, we have 3 features and we have 1 target. So remember, we want to build a mapping between the features and the target. And in our case, we have M examples. So how do we use all of this? How is the data used? And the data is used in batches, and we can define the size of the particular batch. So the batch size can have 2 elements in it, it can have 10 elements in it, it can have 16. And these elements are what we use to do a forward pass through the neural network. In other words, we input the data into the network and we multiply the inputs with the weights, and we apply the activation function. And then we get an output, and then we update the weights. And we'll do that on those particular weights for those particular examples. Then we will select the next batch. So we just jump down and we keep selecting another batch. We push all our data through, and then we calculate the new weight updates. So you can just think of it as selecting small subsets of data to calculate the weight updates. If we select a lot of data, then we're averaging across many examples. So the improvement of weights is less, is averaged over many examples. So it can introduce mistakes. If the batch size is small, then we're averaging over a small number of examples. So we're making a lot of very more precise adjustments. However, there is a trade-off in speed. If we have a small batch size, then it takes longer to process through the data. So this is the main takeaway, is that we process data in batches. We don't just compute the weights on every single example in our data set. We process in small batches. Once we have seen all the examples in our training set, we say that we have completed one epoch. So in other words, we start at the top, we take our first batch, we compute the weights, updates, we take the next batch and the next batch and the next batch, and then eventually we would have seen all the data. Once the full training set has been passed through the neural network, then we say we've completed one epoch. And then we'll do this again for a number of epochs. So it's a very iterative process. And in each epoch, we'll run through all of the batches. And then the number of elements in your batch size is a hyperparameter. So the user specifies the value. And the number of epochs, in other words, the full iterations through all of the batches, is also a hyperparameter. So actually, you'll soon realize that there are a lot of hyperparameters with neural networks. So let's talk about some of the things that can go wrong. And two of the main things that can go wrong is overfitting and underfitting the machine learning model. So, so these are the two. Which one do you think is, actually, I wouldn't have defined it yet, but underfitting is if you are trying to kill a dragon with a small water pistol. In other words, you have a very simplistic model for a very complicated problem. And overfitting is like trying to kill an ant with a rocket launcher. In other words, you have a very simple thing and you're trying to use a very sophisticated model. So these are the two main errors that one might come across when building machine learning models. So underfitting is when your model is too simple, and overfitting is when your model is overly complex. So if we come to the analogy of studying for an exam, and we have three possible options. The first picture is someone reading the course material and then reading 8 more books about the course. The second one is someone reading a single page from the course material. And the third one is someone reading the required material for the course. So which one do you think is underfitting, overfitting, and just right? In other words, a nice balance between underfitting and overfitting. So you can just unmute yourself and try and think, suggest what answer you think it is.
Hello.
Okay, there's a hand up.
Yes, I think numbers are overfitting because the student is basically accumulating so much information for just a single exam. Number 2 is underfitting because they're not learning enough for the exam. And I think number 3 is just right.
Yeah, exactly. That's perfect. So the first example, it's overly complicated. If you're studying for a course, right, you don't need to maybe read every single textbook in existence. But if you're studying for a course, only reading a single page from your course material is far too simplistic approach. And reading the required amount of material would be considered as just right. It's a nice combination between doing too much and too little. So too simple and too complex. So far, you've seen our little pictures that look like this, where we have the inputs, and then we have an output, and then we have the weights that go from the input to the output. But we can add a little bit of complication. In other words, we can now say, well, we can have our inputs, And then we can add a new layer and then have our output. So in this case, we have a 2-layer neural network. We have our inputs coming in on the left as usual. And all of these units are connected to these units in the middle, which is known as the hidden units. It's the hidden layer. And all the weights from the input layer is connected to all the weights in the hidden units. So X1 is connected to all of these 3 circles, X2 is connected to all of these 3 circles, and X3 is connected to all of these. So that's our first layer. And then we can add a second layer, which connects each of the hidden units to the output units. So essentially, we can create layers with many models, right? We're not just restricted to this previous one, where we only have inputs going to the output. We can have models that are much more complex. In other words, we can add more and more layers. So how does it work? Remember previously, we would take our inputs, multiply by the weights, and then apply the activation function. But now we have units in the middle. Now, these units will also have an activation function. Maybe it could be a different activation function to the output one. As remember, we talked a lot about the softmax function, and the softmax function was useful for the output of the neural network. But it turns out that softmax is not used in the middle layers. We use the ReLU layer, which we also talked about. So in this case, we will still multiply the inputs with the weights, but once we have reached to the middle nodes, we'll apply the activation functions, and these activation functions will produce an output value. So now you can think of the output values as the new input to this layer of the network. And if we had more layers, the output of those units would become the new input to that layer. So in other words, the output of an activation becomes the input to the next layer. So let's look at this picture where we have our 4 input units. So we will multiply these input units with these weights, and then we will get output values. So the output values for these 3 units. So this is after applying the activation function. So now once we've applied the activation function, these 3 outputs become the inputs to this layer. So we will multiply the value of the weights by these inputs, and then we will get values for here, apply the activation function, which generates the second output. Now those outputs become the new input to this layer. And then we apply our final activation function, and this is the output of the network. So can you see how we move from left to right, and we multiply the inputs with the weights, which gives us the input to the particular node, the circle. Then we apply an activation function, and the output of that activation function becomes the new input to the next layer. And then we keep repeating this process until we've reached the end. Are there any questions about how we move in a multi-layer feed-forward neural network? Previously, we saw the perceptron, where we only had input units and 1 output, but now it's the same idea, except we have multiple layers. Are there any questions about this? How the output of the units become the input to the new layer? Or alternatively, you can just give me a thumbs up if you are happy with this.
I see some thumbs up, Emmanuel.
Okay, great. Let me minimize this. Okay, so this is the same idea. It's just that I will color code it to be very visual. We have a 2-layer neural network where we have 3 input units, 2 hidden units, and 1 output unit. So in other words, the calculation for H1 will be X1W11, X2W21, X3W31, and then we will apply the activation function to get H1. And for H2, it will be X1W12, X2W22, X3W32. And then we will apply the activation function and get the value of H2. Now we treat those as new inputs. So for O1, we will do H1 times W3 plus H2 times W4, and then apply an activation function. So in other words, we are doing these separate calculations. This is the calculation for H1, where we multiply the inputs with the weights and then apply an activation function. Here's the calculations for H2, where we will multiply the inputs with the weights, and then we will apply the activation function. These become the new inputs, and then we multiply these new inputs with the weights, and we get the final output for the neural network. So if the previous diagram wasn't clear, hopefully this diagram is more clear. So maybe you can give it a go. So here what I suggest is just try to calculate the output for the first example. In other words, when x1 is equal to 3 and when x2 is equal to 2. And the activation function to use here is the linear one. In other words, y is equal to x. So if your input is 10, your output of the activation function is 10. If the input of the activation function is -5, the output is also -5. And then here, what the activation function you could try is sigmoid. You can round your answer if you want, because you might not be able to calculate the precise value of sigmoid. But just remember the graph of sigmoid, what it looks like. Alternatively, what you can do is you can Google. Just go on Google and say sigmoid calculator and find out the value. So is it clear what you need to try? Is just plug in the values of 3 and 2 into the network, multiply, and do a forward pass and try and get the output value. And then maybe someone can walk us through their calculations, and then everyone can check if they are in agreement. So maybe, let's say 3 minutes. And when you have an answer, just pop it in the chat. Is anyone confused as to what you need to do?
I don't see any confusion emoticons, Emmanuel.
Okay, so let's say 3 minutes, and we'll see who can get an answer first.
There is a first answer in the chat.
Okay, so we'll see if everyone agrees or disagrees. Okay, so 1 more minute. Okay, so we have a second answer. And let's see if everyone agrees or not. Okay. Okay, we wait 30 more seconds. Okay, so there's 94.39 sigmoid 1, 1. What about everyone else? 0.5, 0.5. Okay. Any other suggested answers? Okay. Okay, I'm just going to randomly select. So Martin, can you, if possible, unmute yourself and walk us through your calculation?
Hello.
Hello, I can hear you.
All right. So here is what I did. I just took 3 and then I multiplied by 1 and also by -1. And then I added the 2 results, the 2 numbers, which is 3 plus -3, which is 0. And then I took 2 for x2. So 2 multiplied by -2, it's -2 plus 2 times 2, which is what? Which is 4. So the output after all those manipulations is what is 0, 0. And then you take 0 or multiply by what? By -3, you get 0. And 0 multiplied by 3, you get another 0. So you add, and then you pass it through the sigmoid function, which is what? Which is e to the minus x over 1 plus e to the minus x. So it becomes 1 over 1.
Okay, nearly there. Can someone suggest how to get the value for this top hidden unit? So it was nearly there. It was just the logic was switched a little bit. Maybe someone else can.
So for the linear, it's just we just take we retain the input, right? Since we are just mapping x onto x. Sorry,
Sure.
I forgot that one.
No, that's fine. But there was still a small adjustment we can make. Can someone else maybe try to tell me how to get this top hidden unit? So yeah. So the top hidden unit will be 3 times 1 plus 2 times -2. So you look at the connections going into the unit. So that was the difference with what Martin said. It was close. It was just it was a different way. You look at the inputs. So 3 times 1 is the line that goes into this unit. And the other line that goes into this unit would be 2 times -2. Okay.
Oh,
and
nice.
Then yeah. So then, Martin, can you do the second one, the bottom one?
Or the bottom one. So the bottom one, yeah. So we are now taking x1, which is 3, we multiply it by -3, and then we are taking x2, which is 2, and then we multiply by 2. So -3 plus 4, we get what? We get +1.
Yeah, so for this unit, we will input 3, and the connection that goes into this is -1, so 3 times -1. And then the other edge is this one. So we'll say 2 times 2. And then we will add those results. Since it's a linear function, y is equal to x, we don't need to apply any activation function. Then those become the new inputs, which we will multiply with these two values and apply the sigmoid. So I forgot what the answer is. I think it is actually 1, but I haven't got it off the top of my head right now. But I think for the first one, it is 1. So that is how we would do it. Are there any questions, or is everyone happy with the flow of how we go from the input all the way to the output? Can you just give us a thumbs up if you're happy with that, or if you would like us to go through the second example? Maybe if you want the second example, you can do a thumbs down or a confused emoji. Okay, no thumbs down. Okay. So now what's interesting is we can now have many layers, right? We're not restricted to just the perceptron, and we're not restricted to just our example where we had a 2-layer neural network. You can have many, many layers. And the nice thing is now we can finally jump into the buzzword of deep learning. And essentially what deep learning is, it's just neural networks that have many layers, and it's nothing more than that. Of course, the operations will differ from architecture to architecture, and we will look at the convolutional neural network next. But this is the primary idea, is just we keep on adding more and more layers. And I guess to help with the explanation as to why that is useful, without going into a visual example, is, let's say we have a neural network with multiple inputs, and maybe the inputs are some medical readings of someone. So age, blood pressure, weight, and so on and so forth. Now, let's say it's blood pressure, weight, age, height. With these ones I've described, what commonly known calculation can we derive from these terms? So if we have age, blood pressure, weight, and height, what common calculation in related to health can we calculate? It's a fairly common metric. Right, BMI. So if we have someone's height and someone's weight, we can calculate BMI. So you can think of BMI as the circle in the node in the middle. In other words, we use a combination of the height and the weight multiplied by some weights, and we can get BMI. In other words, what we've done is we've abstracted the idea of weight and height, and we've come up with a new metric or formula called BMI. In other words, we've abstracted from the raw input into something more abstract. And this is exactly the idea of deep neural networks, is the input is in the raw form, and by combining them using weights and activation functions, we can come up with new, well, not we, but the neural network optimizes to abstract new functions. And the deeper we go into the network, the more abstract and complex the functions become, because it's now using nonlinear combinations of previous functions. And this is essentially the main idea of deep neural networks, is the abstraction of functions. And as we add more layers, we abstract more and more nonlinear functions. And it turns out that if we do this, we can solve a lot of complicated and interesting problems. So previously on Thursday, we talked about the step activation function, the step function. But in practice, we don't use the step function. In practice, commonly used activation functions are the ReLU function in the hidden layers. So if we consider this little neural network, here A, which denotes these hidden layers, I'm suggesting that you use the ReLU activation function. And for B, which would be the output, the activation function would differ from problem to problem. For a classification problem, you would use softmax most likely. In a binary classification problem, maybe you would use sigmoid. And for different problems, you might use different activation functions. More advanced neural networks use certain activation functions for particular reasons. For example, I believe that some of the networks that are used to generate fake images have a hyperbolic tangent as output in one part of the network. So depending on the network and problem that you're investigating, the output activation function might be different. But for the sake of our time together, the ReLU is the most commonly used one, and for a classification, it will be softmax for all of the reasons we've explained on Thursday last week. So in a regression problem, in a typical regression problem, we would normally have maybe one target variable. So one variable that we're trying to predict for. So we would only have one unit, but maybe we were predicting for multiple numerical values. So we would have as many units as variables that we're trying to predict for, as many numerical values that we're trying to predict for. So if we're trying to predict for rain and temperature, we might have two units here, since both of those are producing numerical outputs. And for a classification problem, we would have as many units as there are classes in the problem. So if we have 10 classes, then we would have 10 units. So hopefully this gives you a little bit of an idea of the structure of the neural network for the two different types of problems, regression and classification problem. For classification problem, you will typically use a softmax activation function. For regression, it depends. It depends on the scale, the range of your output variables. If your output variables are, the target variable you're trying to predict for is between -1 and 1, you could use a hyperbolic tangent function, for example. Or if the range of the values is between negative infinity and positive infinity, you could use a linear function. You can also scale your outputs to be within a range to allow you to use a particular function. So there's many things that one can do. And I don't want to to spend too much time worrying about this. Rather, let's focus on classification. It's a bit easier to understand, and there's less data manipulation issues that we have to worry about. It's just categorical output, and we apply one-hot encoding, and then we use the softmax activation function. So something that I would like you to play around with, maybe you can play around with it now, actually. Yeah, 2:30. Maybe you can play around with it now. Is just go to playground.tensorflow.org, and let me also go there. And okay, so this is what you are presented with, and the main controlling things are at the top, and this is the architecture that you can do. So let's explore some of the areas. Here lets you control the data. So the type of problem that you're trying to solve. Here you can control the learning rate. So you can have a very small learning rate or a very large learning rate. You can select the activation function that you will use. Don't worry about this, we haven't explained it yet. And you can say if you want to try a regression or a classification problem. So let's say we want classification problem. Here you can add or remove hidden layers. And you can add or remove units in your hidden layers. And this is the input space. So here you can toggle what input you want. Do you want to use X1 and X2 directly, or do you want to engineer some features? So something in machine learning is engineering features, where we manipulate the features to try and generate, to improve our model. So here it's X1 squared, X2 squared. And then here, if you wanted to use X1 times X2, you could use this as well. You could have sine as well. So let's say we just want to use X1 and X2, and we as the practitioner, we're not going to do any feature engineering. We're not going to create new data. We're just going to use the inputs as is. And then you click on the play button, which will start the epochs. And then this little rewind button is like a reset. Okay. So here I can see that I've got a model that does well. I can separate the blue circles with the orange circles quite easily. Let's say instead, if I only had one neuron in the hidden layer. Now, I'm not able to separate the data as well. Let's add 2 neurons, but maybe we only use a ReLU function. Okay, in this case, the ReLU function is not able to optimize for this problem. So you can play around. Let's put it back to how it was. Let's leave it as, I can't remember what it was. I think it was hyperbolic tan. No, it was maybe linear. I can't remember. Sigmoid. Okay, so let me just refresh because I want to show you something, a specific example. Okay, so have a look at the loss. The loss is decreasing. But now, what if instead I had a really large loss? So let me reset and let's take a look at the loss. Okay. you can see here there's some extreme fluctuation, and then the loss gets stuck. So now what has happened is, because of the very large loss, I've jumped to an area of the search space and probably got stuck, oscillating in somewhere in the landscape. So remember, we talked about, let me try to find it. We talked about the alpha parameter, which is the learning rate, which dictates how big of a jump we take. Now, you can see from these little valleys, or whatever we want to call them, that it could actually be possible to get stuck. And there's a phenomenon of oscillating and never jumping out. So a large learning rate can result in just oscillating back and forth and never jumping out and just being stuck there. And this is a nice example where this has probably happened. Something else, if we use a very small learning rate, is now you can see the loss is decreasing extremely slowly. And we might actually even get stuck again. However, if we have a slightly more reasonable learning rate, which is not too big but not too small, now we can decrease the loss quite nicely and actually find a solution to the problem. So just maybe spend 5 minutes, come here and add neurons, add layers, see what happens, try a different problem. This one is more complicated, and try and see if you can solve some of these. So maybe we'll just spend 5 minutes on that. And maybe if you have some questions, you can ask your questions in these 5 minutes as well. Okay, so there's a question in the chat that says, how do you know if the model is performing well? So you would monitor some of the metrics for the problem you're trying to solve. If you're solving a classification problem, you might measure accuracy. So is your model getting 30% accuracy, 40% accuracy, 50% accuracy? So you can measure the metrics, but remember, very early on, we talked about having a training set and a validation set. So to truly know that your model is doing well, is you get roughly similar performance in your training set and similar performance in your validation set. So overfitting would be, for example, if you get 99% accuracy in your training set and 60% accuracy in your validation set. So that's not a good model. A good model is one that performs consistently throughout the sets. In the case of a regression problem, you won't be using accuracy. You might be using something like mean squared error or absolute error. There's a number of numerical metrics. So in the case, so the other question is about which metric should you use in the case of an imbalanced data set. So there are metrics which are potentially more suitable that take into consideration both classes. Typically, you would try to avoid putting yourself in a situation where you have an imbalanced set for training. Because if you trained on an imbalanced set, your neural network might just output the majority class and then not train at all. So one way to avoid that is you might oversample the minority class or undersample the majority class, or use other kind of ways to supplement the imbalance, and then you would proceed as usual. So training on imbalanced data is more problematic, and trying to alleviate that via undersampling or oversampling or additional techniques such as the data augmentation would be preferable. So for example, in the case of bioacoustics, if you're monitoring an endangered species, you might have a lot of just background noise. So it's what's referred to as soundscape noise, where you're just recording everything in the background. So you might be in a situation where you have 99% of your data just being, background noise, other animals vocalizing, and you have only 1% of your data that contains the vocalization of the species that you're interested in. In such a case, you can use augmentation techniques to increase the number of vocalization events you have for the species that you're interested in. And one simple way to do that is you can take the clip that contains the vocalization, for example, of the gibbon, and then you can just add many examples of other randomly selected clips of that don't contain the gibbon, and you can do a linear combination of those two things. So you can say 0.8 multiplied by the raw audio data that contains the gibbon plus 0.2 times the raw audio data that contains some other species. And if you plot the spectrogram, you'll still see the gibbon call, but then you'll see the other species calling at the same time. So that's a great way to augment your data set. In typical computer vision, you can use other augmentation techniques such as rotation, cropping. You can translate the image a little bit. You can deliberately add noise. You can add vertical lines and horizontal lines. So depending on the problem you're trying to solve, one augmentation technique might not make sense. For example, if you are trying to augment your data for, you're trying to build a model that can do hand written character detection. If you do a horizontal flip on a 3, it might look like an E. And if you do a flip on a 9, it might look like a 6. So certain augmentation techniques might not work. So you need to think, is my augmentation technique or the approach in dealing with imbalance the right approach? With acoustics, if you're shifting in pitch, that means you're making it more high pitch. That also might not make sense, because then it might not be representative of the data you're trying to solve. So the main thing when it comes to trying to supplement your data by creating synthetic data to deal with imbalance, for example, is to ask yourself if the new data you're creating is representative. In other words, if it's producing data that is similar to the problem that you're trying to solve. If your synthetic data generation is not realistic of the problem you're trying to solve, then it won't help at all. So the follow-up question was about if you have small data and splitting into 70-30. So if you have a really small data set, you might use a different kind of validation approach. You might use a leave one out approach, where you only have one example for validation and the remaining are for training. And then you select another example for validation and the remaining are for training. And you repeat this many times and you average your results. So there are techniques for dealing with very small data sets and how to split it into training and validation. So there's a k-fold cross-validation, there's a leave one out, for example. So if you just Google small data sets and validation, you'll see there's a lot of information about this. And this is probably a topic that a statistician will be able to cover best, because they would be very knowledgeable in these issues. But at least in my research with the bioacoustics, we've found that we can do very well with very little data if we try to use transfer learning, which is something we can talk about in the next session on Wednesday. Okay, so I think you've hopefully had enough time to play with the TensorFlow playground. Is everyone still okay so far? And are you still with me? Can you just give me a thumbs up if you are okay?
Okay, the thumbs ups are coming.
Okay. Okay, so some of you are still with us. So just remember, if you have questions, please just ask. So since we still have some time, let's see if there's any questions about this material first that we've covered on Thursday and today. And if there aren't questions, then we will have a gentle introduction into convolutional neural networks, but let's see for questions first. Please feel free to unmute, or you can also unmute to say that you're okay if you don't have a question.
So Mr. Manuel, can I ask something? Generally, when we create models like deep neural networks, are they only for one specific task, or can we sort of like multi-purpose them for different things, different related tasks?
That's a great question. So this ties in a lot with the idea of transfer learning, and let me just explain it now. So the idea so typically you might have a data set and then you would build a neural network to solve this problem. And if you try to apply this problem to a completely different problem, most likely it won't do well if your input data is completely different and if what you're trying to predict for is completely different. So if you are trying to predict for weather, and then you apply your data. So let's say you're trying to predict for rainfall, and then you apply the same model to predict for stock prices, right? It's completely different application domain. It's not going to work. So that's the obvious one, where you have a data and you build a model specifically for that data. Now, transfer learning is when we have a particular problem and we have typically a lot of data for that problem. So let's say we have 1 million pictures of different things, of different categories. So it's a classification problem. And we build a neural network to classify between the different pictures. Now, since we had so much data and the classes maybe are so diverse, what we can do is apply that neural network to a different problem that is somewhat related. So maybe it has some kind of similarities, and then we would delete the output layer and insert a new output layer and optimize the model on this new problem. And typically in the world of building neural networks for vision problems, where the algorithm is trying to visually do things, this works well. So to give you an example, let's say you have a big data set of pictures of people, and it's a classification problem. So let's say it's pictures of movie actors. And you have, for each movie actor, you have 1,000 pictures. And maybe you have a data set with 1 billion pictures. So now you could build a neural network to do facial identification. In other words, if you give it a picture of someone, so let's say you give it a picture of Francesco, it says it's Francesco. You give it a picture of me, it says it's me. So now your model has learned this. So it's learned visual features of the face. Now, let's say we have a similar problem which is that of emotion detection. So we want to detect if someone is smiling, or if they're frowning, or if they're sad. Now, this problem is fundamentally different, but at its core, it still has the face in it. So we can take the network and we can tweak it in some ways to this new problem where it might have less data. So this is called transfer learning, where we transfer from our original problem that had a lot of data to a new problem that might not have a lot of data, for which the problems are kind of related in some way because they both have to do with faces. And typically academic literature and practitioners have found that this results in strong models and better models had you trained it on the emotion data from scratch. In other words, you built a model from scratch specifically for that problem. And this is particularly true when the other problem you're trying to solve for has very little data. So if your emotion data had very little data, maybe only 100 pictures, and you try to build a neural network to solve that problem, you might overfit. So that's when your model would be too complicated for the amount of data that it has. So to answer your question, yes, we can reuse models, but within reason. If the problems are completely unrelated and the data is completely unrelated, then it might not work. If the problem is somewhat similar and the input types are somewhat similar, then we can get it to work. So hopefully that has answered your question.
Yes, thank you.
Great. Are there any other questions? Okay. So let me then move on to this part, which will be the introduction to convolutional neural networks, which is a specific type of neural network architecture. So far we've been discussing the perceptron and feed-forward neural networks. Now we want to talk about neural networks that can be used for vision problems, where we're trying to build algorithms that can see things. But these same networks can be used for text problems, and it can be used for audio problems. And this is where we can use these techniques for bioacoustics. So let us move on to that. Okay, so this part will be the introduction to convolutional neural networks, also known as CNNs. But as always, it's nice to have a look at some examples. So I want to show you a small, well, two videos actually, as to where convolutional neural networks are used in somewhere in the pipeline. So here is one example of where a convolutional neural network is used in the pipeline. On the left, you have the input to the neural network, which contains a convolutional neural network aspect. And the other side is the result of style transfer. And style transfer basically is you train a neural network to reproduce an input in a particular style. So you provide an image or a video, and then you provide maybe a picture, maybe it's a famous painter, and then you ask the neural network to recreate the input in this new style. So here you can see the input on the left and the style transferred video on the right. So this is a nice example of where some of the ideas that we're going to learn about are used. And here is another one. So now this video is a little bit out of date. So you can see that this is from 2017. Since then, there has been immense progress in this field of research. But I'll just show you this video. And here the idea is we have a neural network that can generate synthetic images. So these images actually are not real pictures. The neural network has learned to create this synthetic images. So you can see that some of them look quite real, some of them look totally ridiculous. Like, for example, this bicycle has this very strange thing here. I am guessing this is an aircraft. It has some very strange things here. And I have absolutely no idea what this is. So some of it looks not at all realistic. But over time, this has improved significantly, especially to generate pictures of people that don't exist. Let's see, right. So here is fake pictures of people. So here you can see initially the network is not, so here it's tasked with producing 8x8, and we're increasing the resolution and we ask it to generate images. And as we increase the resolution, the images look quite realistic. So none of these are real people. And as we keep training the model for longer and longer, the model becomes more and more, well, it becomes better at producing this. And then people have produced these great things that can extrapolate and do all these nice animations. So of course, none of these people are real people. So the network that is used to produce this contains the fundamentals of what we're going to talk about next. And actually, this is a fun activity for you to do after this lecture. Let me just have a look at the time. Okay. So when we're done, just go on your browser and then just look for Google Quick Draw. And it's a fun little activity. It's like playing, I guess it's like playing hangman, where it tells you to draw something, and then you draw it, and then it tries to guess what you've drawn. And the reason that it's so good is that it has access to so much data, and the models could be improved because so many people have participated in this, that you'll see that the neural network will probably instantly guess, will correctly guess what you've drawn, because so many people have drawn that it can tell very quickly what you're trying to draw. So this is just a little fun little activity for you to do later. Okay, so here is a very common computer vision dataset. It's called MNIST, and it is a 10-class classification problem. And the dataset contains hand-drawn characters of digits 0 to 9. And we have like 60,000 of these hand-drawn characters. So it's a very large dataset. And the goal is to read in one of these small images and for the neural network to say, this is a hand-drawn 1, or this is a hand-drawn 5, for example. So what is an image? So an image is essentially just a matrix of pixel values from 0 to 255. A grayscale image contains one channel. So it's a matrix, and it just has pixel values of 0 to 255. And a color image has 3 channels, red, green, and blue. And these matrices are essentially stacked on top of each other. And this is how we can visualize color images on a screen. So you can just think of a computer screen basically as 3 big matrices stacked on top of each other. There's 3 channels, and every little pixel on your computer has 3 values, one for the red channel, one for the green channel, one for the blue channel. So the range of the data is between 0 and 255. Now, we haven't really discussed this, but in machine learning, certain techniques require us to normalize the data. And when dealing with image problems, normalization is an important step, where we just divide everything by 255, since our data ranges between 0 to 255, so we can just divide by 255. And this essentially normalizes the data between 0 and 1. So let's say we have an image that contains 28 pixels by 28 pixels. Now, we could use the neural networks that we've been talking about to solve this problem. In other words, what we can do is we can flatten this image into a really, really long vector. So we take the first row, we take the second row, and we stack it to the right. We take the next row, and then we stack it, and then we create a really long vector, which has 784 elements, because there's 28 times 28. So in other words, we could re-represent a 28 by 28 image into one long vector with 784 data points. So this becomes a problem that we've seen before, and that where we have 784 features. So we would have 784 input units here, and each pixel value would go to a unit here. And then we would have our feed-forward neural network with our hidden layers and our ReLU activation function. And then since it's a classification problem, we would have a softmax output unit here, since it's a classification problem. Now, this is perfectly fine. We can do this, but this is not at all optimal. And we'll discuss a more optimal approach, which is convolutional neural networks. And till this day, convolutional neural networks are the best approach, the state of the art for solving a vision problem and an acoustic problem and a text problem. So it's actually used a lot. It's used in Google Translate. It's used in when you speak to Hello Siri or your Hey Google and all these things. It all uses convolutional neural networks. Okay, so here you can see one of my cats, Coco. So here's a question. Do you think that one or the other, do you think that it would be good to create a model that learns if the top right of the picture contains a cat, if the top left contains a cat, if the middle of the picture contains a cat, if the bottom right contains a cat, if the bottom left contains a cat, or do you think it would be better to have a model that doesn't care at all where the cat is? So is it better to create a model that specifically looks in certain areas, or do you think it's better to have a model that doesn't care where the thing is? It will tell you that it can see it regardless of the location. So which one do you think it is? Do you think it's better to have model 1 or better to have model 2? Okay, so there's some suggestions for model 2. What about everyone else? So there's 50% chance that you get it right. So those are very good odds. Okay, let's have everyone answer. How many people do we have? 30, so 30 answers. Okay, so we have 3 people saying 2, 2 people saying 1. What about everyone else? Okay, 2, 2. Okay, your odds of getting it right are very high. There's very few areas in life where there's 50% chance of getting it right. Okay, so a lot of people are saying 2. So yeah, so it would be better. So 2 is the right answer. It would be better to have one model that can find things regardless of where the object you're trying to find is in the picture. Having a model that needs to look in certain positions, predefined positions, is not as good, because then it's overly complicated. You need to what if the picture size changes? What if it's flipped? What if the object is never in a particular location? So it would be better to have a model that doesn't care about the location of the object that you're trying to find. It can find it regardless of the location. Okay, so how do humans recognize things? So let's say, so here you can see my artistic skills again. Here's a picture of a face. How can you tell that this is a face? So unmute yourself, and how do you know that this is a face? That this drawing here is a face and it's not a picture of a bird. So just feel free to unmute yourself and say, maybe you think that this is a bird.
Because of the basic features that make up the face, and also because over the years, whenever I see a face, it resembles something like this.
Okay. So someone in the chat is shape or appearance. Okay, does someone else want to say, how can you recognize a face? How do you know that when you look at a human, it's a human and it's not you're not looking at a cat with a human body? So we've gone from nitx to very philosophical questions. Okay, so someone says key human features. Okay, that's a great answer. So we can tell that this is a face because our brains are very good at visually abstracting things. We see the two eyes. We see the location of the eyes with respect to the nose. We see the shape of the face. We see the eyes with respect to the shape of the face. We can recognize a mouth. We can recognize the distance between the mouth and the eyes, the mouth and the chin. We can see some hair-like feature. We see the distances. We can abstract all of these small things. And when our brain puts all of these small things, we can see that it's a face. So our brains are very good at abstracting visual things. So the same question with this picture of my dog. How can you tell that it's a dog? So feel free to unmute yourself and tell me how you know that this is a dog. Has no one seen a dog before? So anyone, please just give it a go. I'm sure you'll get the right answer. 99% likelihood of getting the right answer. No volunteers. So you know it's a dog because of, again, you abstracting all these things. The position of the eyes, the fur on the skin, right? So yeah, it's pretty much the same thing. You can abstract the location of the ears, what the fur looks like, right? It doesn't look like human skin. The shape of the mouth, the whiskers, the nose, all these things, when you put them together, you can abstract all of these things and you can say that with a lot of confidence that this is a dog. So this is the same idea with convolutional neural networks, is it abstracts. So the initial layers of the convolutional neural network learn simple things like edges, slanted edges, these blobs, all these very simple things. Then the next layer of the convolutional neural network combines these edges, because remember, we talked about BMI, we talked about using weight and height, and when we combine them together somehow, we get BMI, right? So that idea of abstraction is the exact idea here. The first layers of the CNN learn very simple edges and blobs and very simple visual features. Then we can non-linearly combine them using activation functions, and we can learn more complicated things like an eye and an eyebrow, or maybe a nose, or maybe a mouth. Now we can combine these things again, and we can learn even more complex visual features. And this is essentially what a convolutional neural network is training to do. It's optimizing the weights in the model to abstract. So it's the same with the picture of the car. So the initial layers of the convolutional neural network learn very simple things like lines and blobs. And then these lines and blobs are combined using the weights and the activation functions, and it learns more complex visual things in the next layer. The next layer uses the weights and the activation functions, and it learns more complex things until it learns very complex visual entities. And then we have the softmax layer that now classifies things. And that is essentially the idea of the convolutional neural network, is that we have an image, which here we denote as X, and we have an idea of a filter, which we call W. And here you'll see this operation. So this is not a multiplication operation. This is it's a star symbol, but it here denotes convolution, in particular discrete convolution, so not continuous convolution. And we take an image and we convolve a filter onto it, and it produces a feature map. And I'll explain what this means. But this is the idea, is we have an image, and then we're convolving a filter. The filter is what we're trying to optimize for. We're trying to find the weights of this filter to produce interesting feature maps that can help us solve the problem. So maybe some of you have played around with photography software at some point, and you would have come across something called edge detection. And if you've studied image processing in the past, or maybe you use Photoshop or photo manipulation software, you might have come across that you can do something like this, where all the lines are clearly visualized, and everything that is not a line is darker. So here you can see the outline of this animal is quite visible. Now, what has happened is this image is a color image. So there's 3 matrices stacked on top of each other. And if we convolve this matrix, this 3x3 matrix, and we put it in the left corner, and we do a dot product, and then we generate, and we put the answer here, and we move our little matrix, our filter 1 step to the right, and we do the multiplication, and then we generate the answer, and then we move this all around the picture. This is the result that you get. And before convolutional neural networks was popular, this approach was how researchers used to deal with image classification problems, is they used to handcraft these filters. So there's many of these filters. If you're interested in them, you can Google the Sobel, the Prewitt. There's many of them that have been handcrafted to create these feature maps. And many years ago, this is how researchers used to approach computer vision problems, is they would manually design these filters to produce feature maps. But now with convolutional neural networks, we don't need to manually do this anymore. The algorithm learns this for us. So we have 5 minutes. So let's just talk about the filter. So the filter is what the convolutional neural network is trying to optimize. It's what it's trying to find new weights for. And it has 2 main hyperparameters, which is the width and the height. So you would have to say, I want my filter to be a 3x3 or a 5x5 or a 7x7. So this is a user-defined parameter. A hyperparameter is a user-defined parameter. Now, remember, with the feed-forward neural networks, we had these edges, and we had we had the circles, and we had the edges between the circles, and the edges contain the weights. With convolutional neural networks, the weights are inside the filter. So here's a 3x3 filter, and here are all the weights. There are 9 weights. And these are the values that are initially randomly created, randomly initialized. And we want to optimize these values such that the CNN will produce interesting visual features, which can in turn be used for classification. So here there are two similar words. Hyperparameter is the user-defined parameter where we say, I want the height to be 3 by 3. And here we have parameter, which refers to the weights. And these are what we optimize during the optimization of the algorithm. So it's just good to know the hyperparameter is for the user, and the parameter it refers to the weights, refers to what the neural network is optimizing. Okay, so let's stop here for today. So you've had a little bit of an introduction to convolutional neural networks, and we will resume here. But we have 2.5 minutes. Are there maybe one or two questions?
Yeah, thank you very much, Emmanuel. So far, it was really very interesting. Thank you. Let's see if someone raises a hand. Let's see if there are any questions in the chat.
Is everyone happy with this introduction? Just give us a thumbs up if you're happy so far, and then we can
here comes the question. Mpumelelo, okay. Please, you're welcome to ask your question in person. Yeah.
Thank you very much. Actually, Mr. Emmanuel, I want to ask regarding the CNNs in terms of the architecture and the functionality. Do they really reflect how human beings, how humans' visual process works?
So it's not a true representation of the visual cortex. It is one way to algorithmically produce what our brains do in the visual cortex. So it is not a true representation, but it is a model that allows us to reproduce the ability to abstract. So neural networks takes a lot of inspiration from neuroscience, but it is not an attempt to model the brain. It is an attempt to draw inspiration that our brains have these synapses, and we can strengthen the synapses. And it's fascinating if you study neuroscience and you study neuroplasticity, and some of these ideas in neural networks you'll appreciate them more. But it's mainly about the inspiration from, rather than the attempt to reproduce.
So one can say it's more of like than trying to create I don't know, like a biologically similar sort of like model of vision. Like, is it more of engineering more than anything else?
It's an attempt to be able to create a visual abstraction. Yeah, let's say that.
Thank you.
Cool. Eric?
Eric, yeah.
Thanks, Emmanuel. Thank you very much for the talk. It was quite interesting and quite captivating. My question is, I'm not sure. I just want to hear your opinion. Do you think we can eventually use machine learning to try and go back in time? For instance, we have things like evolution, for instance. Can we then train, models in the process of evolution, and then probably turn it backwards to try and, get images of what humans looked like 20 years ago, not 20 years, millions of years ago? Do you think that will be a possible, or it's from sci-fi or something like that?
So, my answer, and the same thing I tell my students, is anything is possible given enough time. So maybe given enough time, we will be able to create strong animations of past historical events. But I do not know enough about this topic to give a strong answer. But what I can comfortably say is there are other areas of machine learning. One of them is called evolutionary algorithms, evolutionary computation, or genetic programming, for which we draw from evolutionary processes and Darwin's theory of evolution to model certain computationally difficult challenges. So researchers do draw inspiration from nature to solve problems. It's not exactly what you've asked, but it's pretty close. But to answer your question specifically, I don't know of the ability to do this yet, but I suspect that given enough computation, we can generate something interesting.
Yeah, Emmanuel, if we don't have any further urgent questions, Emmanuel's next lecture is, I think, on Wednesday morning. Yeah, but don't forget that we have also 2 interesting lectures tomorrow. Yeah, and tomorrow morning we have the lecture number 4 in the series on Earth systems and climate change modeling. And tomorrow afternoon, we have lecture 4 of the introduction to statistics. So tomorrow we start the 4th round of lectures. So Emmanuel, thank you so much for another very enjoyable lecture. Thank you so much. That was really interesting. And from the thumbs up, I have the feeling that everybody enjoyed it very much. So thank you very much, everyone. I will see you again tomorrow morning, and we will see together Emmanuel on Wednesday morning. So Emmanuel, thank you very much.
Great. Thank you, everyone.
Have a good evening. Yeah, thank you.
Thank you, everyone. Thanks, Francesco. Bye.
Bye. Bye-bye. Thank you.